So we're going to start off with organic chemistry, with basically how our hydrocarbons actually come into play, or how they created. So we're looking at the source of hydrocarbon compounds, right? We know that hydrocarbons mean that they contain both hydrogen and carbon. All right, so the term biogas is formed by the breakdown of organic matter during decay and digestion. Biogas consists mainly of methane. It is produced in swamps, landfills, herbivore intestines, and biogas digesters. All right, so that's one form in which hydrocarbons are created. For natural gases, contains a mixture of over 78% of methane, small amount of ethane, propane, and butane. And then the popular one, crude oil, which is complex mixture of all hydrocarbons that we use to date. So petroleum or crude oil is a black sticky liquid made of mixture of many hydrocarbons with molecules ranging from carbon number over 100 carbon atoms. Crude oil is of no use in its raw form. Once extracted from the earth, it is transported to a refinery for processing. At the refinery, the oil is first treated to remove sulfur. This reduces pollution during the subsequent use of products. All right, so we take out the crude oil from the ground, so we extract it from the ground, and then we refine it to get the portions of gases or oils that we use in our everyday life. All right, so we use a fractional tool in order to separate the different fractions of the crude oil based on their boiling point. Right, so this is how the fractional column looks. Right, so we notice on the left we have the crude oil being heated with a very high temperature, extremely high temperature, right? And because of each oil in our crude oil has a different boiling point. So based on that, the one that has the lowest boiling point, which is at the top, liquefied petroleum, LPG, that one will be sent off first, and it continues going down like that. Right, so we notice between carbon 1 and carbon 4, meaning that these elements or compounds have carbon numbers between 1 to 4. Right, so those will be sent off first, then followed by our petrol, which are used in our vehicles, right? And then we have naphtha, which we use in different chemical compound or chemical products that we use. Then we have kerosene, which is oil which you use in airplanes and jet fuels and for lighting and heating purposes at home. Then we have diesel, which we know we use it in trucks as well as also high power transportation like our trains. Then the lubricating oils, right? The lubricating oils, waxes, or polishes that we use. Then the fuel oil for ships and factories, right? And then finally, we have the residue, which is known as bitumen, right? And bitumen we use on the road as tar to pave our roads, right? So each section gives its different compound that is produced, and we have each use that is important. So you need to remember at least one use for each of these sections, right? And then we look. All right, so we see that the boiling point of our fractions in our crude oil varies between 40 degrees to 350 degrees. So we need a very high temperature of about 400 degrees Celsius in order to get each fraction to be separated. All right, so we look now at cracking, because what we did with crude oil was to actually break it up into its simpler or fractions that it consists of. So what cracking is if we have a very long chain of a compound and we want to get a simpler ones from it, then we can go ahead and crack it, mean that we break it up into a simpler portion, right? And that's what cracking entails. So cracking is a process used to split large molecules into simpler or small molecules. So we have two types of cracking, which is thermal cracking. And by thermal, we use very high temperature of about 900 degrees Celsius to cause the bonds to break. And we have the catalytic cracking, which uses lower temperature and a catalyst. Right? So this process is an important source of alkenes, since cracking almost always produce a mixture of alkene and alkenes. Right? So cracking produces mainly, or you can say only, alkanes and alkenes compounds. Right? So that's how hydrocarbons actually come from, especially with the process of the crude oil refining. All right, so let's look at organic chemistry starting now, since we know where our organic compounds are from. All right, so we see that organic compounds belong to a group of compounds called hydrocarbons belong to a group of compounds called organic compounds. This ability of carbon to form big molecules has enabled nature to form living matter from simple cells to complex cells. Gasoline or petrol is a mixture of hydrocarbons and is used primarily as fuel in internal combustion engines. All right, so these are just talking about carbon or electronic configuration of carbon, which is 2,4. So that means it can bond with 4 of hydrogen. So these bonds can be either in the form of rings or chains of different size. It can be branch or unbranched in terms of their chains. Right? So we only look at the branches, the chain ones at this level, right? So these are examples where carbon can bond with carbon and then is filled out with additional hydrogens, right? So we know that carbon now, since it requires 4 other bonding to elements, it can actually foster a single bond, right? A double bond as well as a triple bond. Right? And these cases where it will bond with itself in a single bond mode manner or a double bond or a triple bond manner. So a compound that contains only single bonds between its carbon and carbon atoms is called a saturated compound. And it's called saturated because it has the maximum number of hydrogen that it can hold, right? So they can be branched, unbranched, or in a ring format as well. All right, so then we look at unsaturated compounds where now we have, instead of a single bond, we have either a double bond or a triple bond, which will cause it not to have the maximum number of hydrogen that each carbon can hold. All right, so now we look at the functional groups. Right, so the functional groups are the unique aspect of these compounds that give their different chemical properties. Right, so each of our homologous series, which basically are different sections of compounds that has their functional group that gives them their chemical properties. So we know that alkanes from our series only contains a single bond between our carbons, right? And our alkenes have their double bonds, alkynes have their triple bonds. Alcohols have a OH bond to link to a carbon. The carboxylic acids have a COOH bond to, and the amines or the amino group has a NH2 bond. Right? So these are the main homologous series with their respective functional groups that exist as hydrocarbons. Right? There is esters that are there, which we'll be looking at later, which is a combination of 2 of these, right? So let's look at some questions before we look deeply into each functional group. All right, so it said divide the following substances into organic and inorganic compounds. All right, so let's go. So KNO3, would KNO3 be organic or inorganic, right? Any answers for KNO3? Is that an organic or inorganic compound?
Inorganic.
It's an inorganic. All right, B, HCl,
Inorganic.
inorganic. C, CH4,
Organic.
organic. And D, CO2,
Organic.
organic. Are you sure about that one? All right, so someone says inorganic. That's correct. All right, so CO2 is inorganic. Uh, and why is it inorganic? Any answers? Why is it CO2 inorganic? Because there is no hydrogen. Great. All right, so there's no hydrogen there, so it is inorganic. All right, so E, ZnNO3, bracket 2, that is inorganic. And the last one, C3H8, which is organic. All right, great. Question 2, name the functional groups in each of the following molecules. All right, so A, what functional group does A has? Carboxylic acid, great. All right, because it has a COOH at the end right here. So that's the functional group of carboxylic acid. All right, so B, what functional group is present? Alcohol. All right, great, because we have at the top there, we see there is a OH bonded to a carbon. And then C, what will C be? Ester. All right, so I know someone is going to say that. All right, so it's not an ester. All right, this compound has, basically it has three functional groups. It has an alkene from our double bond between carbon carbon. It has a OH, which is an alcohol, and it has a COOH, which is a carboxylic acid. Right, so it's not the ester, right? So ester has a different functional group, which we're going to look at entirely. Right, so in this case, we're just highlighting all the possible functional groups there, which is an alkene for the double bond, OH alcohol, and COH for ester, for the carboxylic acid. All right, so the last question is to divide which is saturated and which is unsaturated compounds. All right, so A is would be a
Saturated.
saturated, because, and B
Unsaturated.
unsaturated for B. Yes, that's correct. And C is
Unsaturated.
unsaturated. D would be for D. Any answers for D?
Unsaturated.
Unsaturated? No, that's
Saturated.
it is saturated because there is no double or triple bonds there. It has a maximum number of hydrogens to the carbon. And E would be
Unsaturated.
yes, it is unsaturated. And finally, F would be
Saturated.
saturated. Great. All right, so those are the simple parts of hydrocarbons and organic chemistry that we're required to know. So let's now dwell into each of these different types of compounds. All right, so looking at each homologous series. So homologous series is a group or family of organic compounds that has the following characteristics. They have the same general formula, they have the same chemical properties, they have the same functional group. Each member differs from the previous one by a CH2 characteristics, and they show a gradual change in density, viscosity, flammability, melting point, and boiling point. Right, so all the compounds from a specific series has all these things in common, regardless of their functional group. All right, so general formula is a simple algebraic relationship between members of each element or in a compound. All right, so we know that alkanes have a general formula of CnH2n plus 2. Alkenes have just a CnH2n. Alcohols have CnH2n plus 1 OH. Right, and we know alkynes, it's not there, so alkynes have a chemical formula of, anyone? What's the formula of alkynes? Anyone? The general formula of alkynes? No one? All right, so the CnH2n plus 1. No, not quite. All right, so alkynes have a CnH 2n minus 2, right? So it's the opposite of our alkenes. So instead of a plus 2, we have a minus 2 present, right? So that's for alkynes. Sorry. Right, so a functional group is a group of atoms that are responsible for the chemical properties of a homologous series, right? Which we've been through these already. All right, so let's look now at naming our compound. All right, so in naming our compounds, we know that we have different prefixes based on the number of carbons that are present in our compounds. All right, so let's just run through to see if we do remember. All right, so when it's 1, so help me out now. When it's 1 carbon, then the prefix is meth, great. When it's 2, then it's eth. When it's 3, it is prop. When it's 4, it is. When it's 5, it is pent. When it's 6, it's hex. When it's 7, it is. What's there for 7? All right, so we're having a pause for 7. All right, let me help you out with 7. So 7 is hept. All right, and then 8 is oct. 9 will be, so 9 is none, and 10, which is the max that we do at this level, is dec. All right, so those are important to remember and know because it helps you in naming each individual compound, right? So it's in naming our compounds or writing the formula of the compounds. So in naming our compound, we look at the amount of carbons that's present and we look at the functional group that's there in order to name it. All right, so let's look at some examples. All right, so if we look at the example propane, all right, so because it ends in A and E, then that means it's an alkene group, right? So in that case, we have C3, right? And we get the 3 because the C there, the prop is when it's carbon 3, right? So in that case, alkanes have a general formula of CN H2N plus 2, right? So in this case, N will be equal to 3, right? So we have C3 because H is 3, N is 3, sorry, H, then we have 2 multiplied by 3 plus 2. All right, so we do the multiplication first. So it is C3, H3 times 2, which is 6. Then we add the 2. So that's how we get the C3H8, right? And then for ethene, then we know that F is our prefix, which therefore N will be now 2, right? And this is ene, so ene means that's an alkene. So that's where the general formula is CnH2n plus 1. No, sorry, there's no plus 1 here. So it's just H2n, right? So in this case, N is 2, so it's C2H2n, which would be 2 times 2 gives us 4. And that's how we get that as our formula, right? So it's the same for any compound from any functional group. Once you remember the formula, the general formula of the homologous series or functional group, then we just substitute the numbers based on that. So that's how to name our compounds. But in terms of the structure of these compounds, right, we have our molecular formula C3H8 that we just did. So that means we're putting 3 carbons, right? And because it's an alkene, the carbon-carbon bonds will be a single bond. So we notice that between each carbon, there is just one bond between each carbon, right? So we see that there's just one bond here, one bond here, right, between our carbons. Now to fill out, since an alkane, the other bonds will be hydrogen, right? So if we look at this carbon here, when we have this bond between this carbon, then that means it utilizes one of the four, right? Because remember, each carbon can accommodate 4 bonds. So it uses one of the 4, so that means we need 3 more bonds here. So that 3 here will be the amount of hydrogen that you will bond with this carbon. So we have 1 hydrogen bond there, 1 here, and finally 1 there. So this carbon now has 4 bonds with it to make it full, right? And then we look at the next carbon, which is our center carbon here, right? And we notice our center carbon has 1 bond already utilized with this carbon, and it has a next bond here utilized with this carbon. So it needs 4 bonds to be made. It utilizes 2 bonds already, so therefore we need 2 more bonds to be created. Right, so these 2 bonds will be done with a hydrogen, 1 here and 1 there. And finally, for the last carbon, which is this carbon here, we notice that it has a bond with this carbon, right? So that means it utilizes one of its bonds already, so therefore it needs 3 bonds, which that means we have 1 carbon here, 1 hydrogen, sorry, 1 here, and 1 there, right? So it's easy to break them like this because when the structure is large, sometimes it's hard to remember how many bonds we need to create on each carbon, right? So we isolate each carbon and then we work from there, right? It makes it easier for you not to get confused in drawing the structures, right? So that is your structural formula of the alkane, and sometimes they ask you for the condensed formula. Now the condensed formula tells you exactly the order in which each hydrogen is to each carbon, right? So this is your molecular formula at the top, which just tells you how much carbon is there, how much hydrogen is there. But your structural formula tells you on this carbon how many hydrogen is present, on this one how many is there, and such, right? So if we draw the structure, we notice that on this carbon right here, we have 3 hydrogen present, right? So that means we have a C and then 3 H's, right? Then we have the middle carbon, which is 2 hydrogens present, so therefore the middle carbon, then H2. And then on the last carbon again, we have 3 hydrogens present, so that means we have H3 beside that carbon. So it tells you exactly where each hydrogen is present in our formula. So that's what the condensed formula tells you. All right, so we've done these prefixes. All right, so we notice that our alkenes all ends in ane, our alkenes ends in ene, or alcohols end in null or annual, and our organic acids ends with enoic. Right? So it's important to know the ending of each, because once you have your prefix and the ending of each, you put both together to give you the name of each structure. All right, so let's look at these here. All right, so write the displayed structural formula, right, which is given of each formula, right? So we notice that for methane, it's an alkane, so it's CH4 because meth is 1, right? So it's just 1 C and 4 hydrogen, and that's what we see in our structure here, right? So we have 1 C and 4 hydrogens bonded to it, right? The next is methane, so meth means 2, so 2 carbons, right? It's an ane, so that's an alkane. So we have 6 hydrogens present. So we have 2 carbons with a single bond between because it's an alkene. And then for each, we fill out the other remaining bonds with hydrogen. We have propane, C3H8 because prop is 3, right? It's also an alkane, so that means each carbon-carbon bond will be a single bond, and then we fill out with the hydrogens. Butane is the same, right? So it's just to highlight which functional group is there and the prefix to know how many carbons will be present, right? And let's look at the or alkenes, right? So we notice that it ends with ene, so that means it is an alkene, right? So we use our general formula to get our formula C2H4. So in this case, we have two C's, and because it's an alkene, we have a double bond between our C's, right? And if we isolate each carbon, right, we notice before these two hydrogens are placed, it has two bonds already, right? So that means it needs two more bonds to accommodate hydrogen. And the same thing for this one, it uses two of the four bonds already, so we need two more hydrogens to create a structure that is full, right? So that's for ethene, same thing for propene. So propene is 3 carbons, right? Now, for alkenes and alkynes, the double and triple bonds respectively are for just one, right? So it's not more than one double or triple bonds in the structure. So we only can have just one double bond or one triple bond in your structure. So in this case, we have a double bond between these two carbons, right here, and then we have a single bond between this carbon right here. So that doesn't mean that this is an alkene and this is an alkene, right? So this is entirely an alkene because it has a double bond present in its structure, right? And then we do the same again, we isolate each carbon, so we notice this utilizes 2, so it needs 2 more hydrogens there. The middle one utilizes 2 here, so it needs 2 more, right? And then the final one utilizes only 1 with this carbon, so it needs 3 on its outer shell, right? Now, so that's how you do it for alkenes, alkynes, alkenes. The same process still applies. All right, so these things we have done, our general formulas, the endings of our names, right? And then our alcohols and acids, imines. All right, so now let's look at naming our branch chain compounds, because what we just did was to name our on-branch chains, right? So we have different steps that we take based on the type of functional group that is present, right? But the first thing to note is that when we have a branch off, then the branch that is there is normally has a different name. And it depends on the amount of carbon that is present as well. So the 3 types of branches that CSEC uses would be a methyl, which means that it has a 1 carbon on that branch. Ethyl, that means it has 2 carbons on that branch, and the propyl means that we have 3 carbons on the branch. You can use other compounds like halogens, like chloro or bromo or iodo as or branches, right? So those are important, right? So, and also if you have more than one branch, then you note if you have more than one methyl branch, right, you need to show that it's 2 methyl branches that you have, you use di. If it's 3 methyl branches, you use tri, and if it's 4, you use tetra, right? And we're going to look at each as we go along. All right, so let's look at each of these branches respectively. All right, so the first one here. So the first thing that we do is to first note if we have a branch or not. Now, a branch means that if you're counting between carbons, you can make a 1, 2, 3, 4, 5, 6 straight counting without skipping a carbon, right? So that means that there is no chain. That's a chain So there's no branch. So that's unbranched, right? So unbranched means you can move from one carbon to the next continuously without skipping a carbon. When there is a branch one, then that means that you count and there is at least one carbon that's not in your consistent counting, right? So let's look at this one. So the first thing, that's what we need to check, if there's a branch or there is no branches, right? So if we start counting here, that's one carbon, that's two carbon, that's three carbons. We notice that we skipped the carbon here, right? So if we do the same, and go this side, we notice that there's still a carbon that is not in our continuous counting, right? So that shows us now that we have a branch compound, right? So we identify that's a branch compound. The next thing is to note what type of functional group it has, because that will actually allow or vary in your results based on the name. So we identify if it's a branch, which we did. Now we identify what type of functional group is present, right? And based on that structure, what type of functional group is there? Yes, what type of functional group is present right here? An alkane. Yes, it is an alkane, right? Because we notice that between each carbon bond, there is just one single bond there. So it's an alkane that's present, right? So we identify the functional group that's there. Now we're going to name our carbons, right? Because we need to name the longest chain that is possible, right? To know where the branch is. So we're naming the longest chain possible, and the chain does not mean it has to be a straight line. It just needs to ensure that it's a continuous numbering of carbons, right? So we notice there's 4 carbons here, right? So if we name 1, 2, 3, that would be our longest chain, right? So, and also you number your carbons closer. You put the number closest to the branch. So that means when you have your carbon, so we notice that the branch is on carbon 2, right? It should be the lowest possible number for the branch to exist, right? So because this is just 4 carbons, if you number from this side or you number from this side, 1, 2, 3, or 1, 2, 3, at any point, the branch is on carbon 2, right? So it doesn't matter where you number from in this case, because all will have the same branch, which would be on number 2. All right, so now that we know that the branch is on number 2, right, then we need to know what the name of the branch is. So we notice that this is our unbranched chain here, so that means this here is our branch, and this branch is called, what's the name of this branch? A methyl branch, right? Because it only has 1 carbon present, right? So now we have the number of carbons in the chain, we have the name of the branch that is there, we have the number of carbon that is present on. So that means we are going to tell the person that's reading that it's on carbon 2, right? So we put a 2 there to show that it's on the carbon 2, right? We put a dash, and then we tell you the name of the branch that's there, and the name of the branch is a methyl branch, right? So we're telling them on carbon 2 there is a methyl branch, right? And then we tell them how much other carbons in your chain that's present, and we have 3 carbons in this chain. So therefore 3 carbon means that, what's the prefix for 3 carbons? Prop. So that means we have prop because it's 3 carbons in our longest chain. And then the final thing is to know which functional group it is, so we know what the ending will be, and we identify that it's an alkane, so that means ENE at the end here, right? And that gives us the name of this branch compound to be 2-methyl propane. All right, so is that clear? for everyone?
Can you go over how you got the 2?
Sure. All right, so we got the 2 from naming our longest continuous carbon-carbon chain, right? So we need to number the carbons to ensure that the branch is on the smallest possible number, right? Now, because this is just 4 carbons, then that means we have 3 carbons that will be the longest chain, right? So if we number from this end, 1, 2, and if we go to the right to be 3 or to the left to be 3, then we notice that if we go here, 3 here, then that means this branch here is our branch, which is on carbon 2, right? So in any form of numbering, the branch will only exist on this 2 right here, right? So this will always be carbon 2. So we're not able to change this from being carbon 2 because of the number of carbons present. So the branch will always be on carbon 2, so that's where the 2 comes from, to tell us that on carbon 2 of this compound, we have a branch that is present. All right, is that clear? All right, so that's the first one. All right, second one. All right, let's go through this again. All right, so the first thing is what's the first thing we need to do? Identify the functional group. All right, before we identify, that's a good one, right? But before we identify the functional group, we need to know if it's a branch. But we're doing this, the instruction says it's a branch, so we know it's a branch. But we need to prove, because sometimes in your exams, they're not going to say it's a branch one. So you need to ensure that that's the first thing you look for. Is it a branch compound, right? So remember, we check the carbons to see if we can have full numbering of all carbons. If we can have full numbering of all carbons from one to the next, then that means it's not a branch one. So let's go. So we go 1, 2, 3, 4. Right? We notice we have 4 continuous and there is 1 missing. Right? Even if we started here, 1, 2, 3, 4, we still will have 1 missing here. So that shows us that we have a branch. Right? Then now we look at the functional group, right? And what functional group is this? An alkene, right? Because between each carbon bonds, we have a single bond present, right? So we identify that is a branch, we identify the functional group. Now we need to know what's the next step. Yes, what's the next step that we take? Since we have identified the functional group, identify the number of the carbons with the branch, right? So now we need to number carbons to ensure that the branch is on the smallest possible number carbon, right? So we know that either the branch is this one carbon here or this one here, right? Because so therefore we can, if we start numbering here, this is a 1, 2, 3, and if we go 4 here, that means the branch will be on 3. Right, but if we start from this side, if we see this is 1, 2, 3, 4, then the branch is on 2, or if this is 1, 2, 3, 4, the branch is still on 2. So therefore, we start numbering from our left-hand side. So I'm going to do it from the top down. So 1, 2, 3, 4. All right, so we see that our branch now is on the second carbon right there. All right, so now we identify the branch that it's on, which is, what's the name of that branch? A methyl branch. All right, so now we have all the things needed to name our compounds. So therefore we write that it's on carbon 2, right? Then hyphen to tell us what's the name of the branch, which we know is methyl, right? And then we tell them how much is on our longest chain, which is 4 carbons, and 4 means that it is bute, right? And we know that it's an alkene, so that means it ends in E-N-E. All right, so is that clear? Any questions on this one? All right, great. All right, so I'm giving you this one to do. No, I'm not. This one is a little bit difficult because we notice it's the same one as the second one, but we have a we have a Cl there on the same carbon. Alright, so it's the same as the second one, but in this case, instead of a hydrogen here, we have a chlorine right here. Right? So we still know that this is carbon 2, right? And we're taking this is our branch, right? But in this case, we have two branches. So we have a methyl branch and we have a chloride or a chloro branch, right? So we state that we have 2 on atom 2 because we have two branches on atom 2, or carbon 2, sorry. We put 2, comma 2 to show that we have two branches on the carbon 2, right? Then we put the hyphen, then we name our branches, right? So you can methyl or chloride, it doesn't matter because both of them is on the same carbon, right? So you can put methyl first or carbon first. Some books you'll see once it's on the same carbon, right? So methyl, or as someone put chloromethylbutane, right? Which most books you'll see it in that order. So let's do it in that way. So put chloro because we have a chlorine bond there. So chloro, methyl, and again the longest chain is 4, so that is butane, right? So it's sometimes there, so you have to look, especially because sometimes you're just skipping through and seeing a lot of H's, so you think that everything is an H, right? So you have to look to ensure that all carbons are linked to a H, right? If not, then if it's a halogen, then you have to add that in your name, right? So the halogen, once a halogen is present, the name, it has to be present in the naming of the compound. All right, a question, can explain why there are two twos in front. All right, so the two twos are because we have two branches on this structure. So we have this branch, which is on carbon 2 right here, right? And we have a chlorine or a chloride branch on it as well. So we're telling the person that we have two branches on carbon 2, so we put 2, 2, right? Now, in some, I think some persons would accept if you just put 1, 2, and then put chloromethylbutane, right? Which is, there's nothing wrong with that. But at this level, it's good to practice to use that because you put two twos, it's showing you that we have two different branches on carbon 2, right? So it's telling the reader that on carbon 2, there is a methyl branch there and there's a chloride branch there as well. So that's the purpose of the 2, 2. All right, that answered the question. All right, great. All right, so let's see. All right, so it's the same when it's a condensed structure. All right, so I'm going to ask you to do, all right, so there is none here. We're going to try one. I want to do one with an alkane, so alkene. So let me draw one here and we can do that together. All right, so I'm not going to fill that. Let me try to fill out all the H's here, which is going to take some time. All right, so we have this structure here. All right, so you're going to direct me into doing this because once we can name this, then you're on your way of naming any branch or unbranched structure. All right, so directions, what to do first. All right, so look for a branch. All right, so great. So remember, we start counting to see if we have a branch present. All right, so if we start from this side, this is 1. All right, that color is fading. So this is 1, 2, 3. If we come here, that's 4. That means we miss out 2. If we continue 4, 5. All right, we still miss out 1 here. So that means we have a branch. All right, so that's the first step. So we have a branch. Next step is to the functional group. So we identify the functional group, and what's the functional group here? It's an alkene, and it's an alkene because we have a double bond present right here. All right, so now we have an alkene or functional group. Great. All right, so what's the step from there? So after we identify the functional group, then we number the carbons. All right, so this is where it gets confusing to some students, right? Now remember, when it's an alkene, we start counting from the side that's closest to the branch, right? But when it's an alkene or an alkyne, we start counting closest to the carbon with the double or the triple bond. So that's very important. So that's why I'm doing this one. All right. So once you have a double or a triple bond, you start counting from the side that has the closest to the double or the triple bond, right? And we note based on our numbering before that the maximum number in our chain will be 5, right? So in this case, we will never start counting from this side, because if we start counting from this side, we're going to say that the double bond is on carbon 3, right? So we know that it's on 3, but if we start counting from the left-hand side, we see that it will be on carbon 2. So therefore, the correct one that we will use will be that it's on carbon. So we start from our left side when we're numbering, right? So everyone understand that? Why we start from the left? All right, great. All right, so now that we have our starting point, so we have our number 2, so it's on number 2, right? And therefore we identify now our branch chain, which we see that if we have 5 going across there, then this down here is our branch. And the name of that branch would be a methyl branch, right? So now we have all the things that are needed to write our formula. So let's go. What's the first thing I will write in naming this? All right, so we tell them which which carbon the branch is on. Right? I'm seeing someone has 2 methyl. It's not on 2. Our branch is on 3. Right? So our branch is on 3. So therefore we have 3 dash methyl. So we're telling them on carbon 3, we have the branch, which is the methyl branch present, right? And then we're going to tell them how many carbons are in our long chain, which is 5, and 5 means that it is pent, right? So it's pent because we have 5 in our long chain. And then the purpose of why we circle the 2 there is to tell them that on carbon 2, there is a double bond, right? So that means that after the pent, we put a hyphen, then we put 2 to symbolize that that's where the double bond is, then hyphen again, and then we finally tell them that this is a double bond, so we put "ene" at the end. So the 2 here represents that it's on carbon 2. The "ene" tells us that it's a double bond and not a triple bond present. All right, so is that clear in this name? Yes? All right, great. All right, so this process follows every single structure that you name for any hydrocarbons, compounds, right? And at this level, there is nothing that will deviate from anything that we just did. So once you follow those steps, you'll be able to answer any question for any hydrocarbon that is there. All right, so let's move on. All right, so let me just clear up some things here. All right, so the last thing for this section, we are going to talk about isomers. All right, so we should be able to finish this before the time expires. So isomers now tells us our organic compound with the same molecular formula but different structural formula, right? So isomers tells us that we can have the same formula, So we can have C4H10, but it's arranged in different structure when we're drawing it. So isomers that are in the same homologous series have similar chemical properties, but different in their boiling and melting point. So because it varies on their structures, then that means their boiling point and their melting point can also be different. But their chemical properties are the same because it has the same atoms, carbon, hydrogen. It has the same, if it's an alkene, it will have the same double bond, but it's just the difference in where the setup is actually in. So let's look at this one here. All right, so we see that we have the functional group of our OH, which is an alcohol, right? But we have, so at each crossing, there's a carbon there. So we have 3 carbons, right? So in both cases, we have 3 carbons. In both cases, we have the same amount of hydrogen and a OH. So that means we have the same formula. So the formula here will be, so we have C3s, right? And then we have 1, 2, 3, 4, 5, 6, 7. So 7 H's, and then we have the OH, right? So both structures here, that's their general formula, right? But we see here that in the first one, the OH is on this carbon atom here. And in the second one, the OH is on the second carbon or the mesocarbon in the formula, right? So because of that variation in the structure of this compound, then we say that it's an isomer, right? So both has the same amount of carbon, hydrogen, and oxygen, but they will have a little variation in terms of their boiling or their melting point because of their structure arrangement, right? So in these cases, what changes would be where you put your functional group, right? So in this case, if you're writing the formula of this alcohol, it's 3 carbons, right? So you name it and tell where the functional group is. So this one is on carbon 1, and in this name, you say that it is on carbon 2. So the name is different, but the amount of each atom in the formula is the same, right? So that's what isomers, the structural isomers, actually are. All right, so let's look at butane, right? So we see that on the left one for butane is just one long chain here with 4 carbons, right? And we have 10 hydrogens present. On this one here, we see that there's a branch, right? So there's a branch on carbon 2, which is a methyl branch. So in naming this is a butane, the regular name butane, right? But if we're supposed to name this structure here, it will be that it's on carbon 2, and it's a methyl branch that is there. So 2 methyl, and then this is 3 carbons, and 3 carbon is prop, and it's an alkene, so that is propane, right? So we see that the name of the formula can be entirely different, which can somehow trigger off that, hey, this is probably something different from the formula of butane. But when you recognize that it has the same number of carbons, which is 4, and it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 hydrogen, it's the same as butane. Right? So in these two cases, this tells us that it is these two compounds are isomers of each other. Right? So butane and 2-methyl propane are both isomers. Right? So is that clear with everyone? All right, great. All right, so let's look at these questions and then we can finish off with this. All right, so the diagram below shows the structural formula of an organic compound. Name the organic compound. All right, so we notice there is no branch here, so it's not a branch structure. It has a double bond, so it is an alkene. And alkene, sorry, right? Because there's a double bond here. And if we number where the double bond is closest to, it's on number 1, right? So we can actually say that this is 3, which is prop. So it's prop. So most persons will write propene, which is not wrong, all right? But if you want to be more specific, you can say that this is prop 1ene to tell them that it's on carbon 1, right? So prop 1ene will be specific to say that the double bond is on the first carbon, right? Name the homologous series to which this compound belongs, which we know is an alkene. Classify the compound as a saturated or unsaturated compound. So is this a saturated or unsaturated?
Unsaturated.
It's unsaturated because of that double bond. Then write the molecular formula of the compound, which we just did. Well, no, the molecular formula, right, would be how much of each carbon and hydrogen present. So in this case, we have 3 carbons, right, and then we have 6 hydrogen. So that would be your molecular formula to tell how much carbon and hydrogen are present. All right, and the same thing applies. Now, before we finish with isomers, to know the amount of isomers that a formula can entail is, let's look at a compound that has 5 carbons. To tell how much variation it can be, an easy way is to actually eliminate the 2 carbons at the end, and you get a 3 variation in that. Say if it has 5, you can have 3 variations of isomers, right? If it has 6, you take away the 2 ending ones, it has 4. If it has 10, take away the 2 ending ones, you can get a positive. So in drawing the structures of those isomers, you can vary the location of your branches, right? So if it asks you, you have 5 carbons, right? So you have pentane, and you need to draw 3 structures, the 3 isomers of pentane. The first part is to draw the regular pentane, which is a chain, and then you start drawing the branches of pentane, right? So you can have a branch on atom 2, carbon 2, and then a branch on carbon 3, right? So changing the location of your branch is the easiest way to actually memorizing how to draw your structures of your isomers. All right, so let's look now at each individual functional group, especially for their reactions in certain situations. All right, so because we have done some of these already. All right, so we did these things already, so it makes it easier. All right, so if you look here in this table at the boiling point, we notice as we increase the number of carbons, the boiling point increases. Right, so it starts from negative 162 and it starts to increase gradually once the carbon amount increases. And that should be obvious because we're increasing the number of bonds present in each compound with an increase in carbon. All right, so that's something to remember. All right, so we did these already. Now let's look at the chemical properties. All right, so alkenes are generally unreactive. Yes, it will be posted. All right, so they are generally unreactive due to their saturated carbon-carbon bonds, but however, they can undergo 2 types of chemical reactions. So because they are already stable, meaning that all carbons have the full amount of bonding present, but they can undergo combustion, meaning that they can burn. The alkanes undergo combustions in air or oxygen to form carbon dioxide and water vapor. The following 2 equations illustrate such. So in this case, we have methane. We burn methane, so that means there's O2 present, and it gives us carbon dioxide and water. All right? So so alkanes undergo combustions to give us carbon dioxide and water. Or we can have a substitution method or substitution reaction. So it's substitution because we're taking away a hydrogen that's there and we're replacing it with another compound, with another element, preferably a halogen, right? So it undergoes substitution reaction, right? And in this case, with if it's been replaced by a halogen, such as fluorine or chlorine or bromine, we have to have UV light present or heat to form a mixture of the halogen alkane, right? So in order for this to happen, you have to have heat or UV light. The purpose of that is to give it enough energy to break that hydrogen carbon bond so the hydrogen can be released and so you can have the halogen being bonded to the carbon. All right, so in this case, we see that methane reacts with chlorine and we get chloromethane and we have HCl, right? So the hydrogen that is released from methane bonds with a chlorine from the chlorine gas, and one of the chlorine from the chlorine gas bonds with the methane. All right, so we notice whatever amount of carbon there is, it's the same. It produces, so, sorry. So it produces, a hydrogen is removed and the chlorine takes that place, so that's why it's called substitution. Now, in the presence of a lot of the halogen, right, and we have a continuous reaction just like this reaction will continue. So when we have CH3Cl being formed first, if it still has enough chlorine present in that mixture, it's going to react again with chlorine, so we can add another Cl to it. So now we have two Cls, right? And if we take this and we have more Cl2 present, and we continuously have a reaction until all the hydrogen are replaced, right? So once you have enough of your halogen present in the presence of UV light, the reaction will continuously occur until all the hydrogens are removed. Right? So in this case, we will get just CCl4, right? Because there is a continuous substitution happening in these cases. All right, so it's important to remember that no reaction occurs in the dark, but the reaction is explosive in sunlight. The sunlight provides the start of energy, which is your activation energy for the reaction to occur. If bromine is used, a visible sign of this reaction is a rapid decolorization of the bromine color, changing from reddish brown to colorless, right? So that's how, and further on, we'll note that that's how a method of checking if a compound is saturated or unsaturated, by reacting it with bromine. Because once it is saturated, it's going to change bromine's color from a brown, reddish brown color to a colorless compound because it's replacing hydrogen in your alkanes. All right, so we look at uses of alkanes, which we did before. All right, so methane, we use methane for production of ammonia or natural gases. Gasoline, we use it as solvents, as paraffins, right? Lubricants. And we use it as fuels, which the ones for cooking, so methane for cooking, or the LPGs, right? So those are, but a negative use of alkanes are the substitution alkanes such as chlorofluorocarbons, which are commonly called CFCs, which are non-flammable and not very toxic, used as refrigerants, repellents, or for carousels, making polystyrene, right? Solvents for dry cleaning or general degreasing purposes. So unfortunately, CFCs are largely responsible for destroying the ozone layer. So CFCs are important Well, it's important for some everyday usage, but it has a negative impact on our environment, right? So it actually depletes our ozone layer once it is being produced. All right, so these are the basically what we did was to just look at the reaction of alkanes, which we did the structures and the names before. All right, so just to recap, alkanes react by combustion by producing carbon dioxide and water in the presence of oxygen, and it actually involves in the substitution reaction where it can be replaced by a halogen, a hydrogen can be replaced by a halogen in the presence of UV light or just heat. All right, so let's look now at our alkenes. So again, we already looked at naming our alkenes and drawing structures with alkenes. We know the general formula, CnH2n. All right, and the same thing applies in your boiling point of our alkenes. We see as the number of carbons increase, our boiling point also increases. All right, before we move here, something important. The first three alkenes are gases, the next few are liquids, and the rest are solids. All right, so we start off with the first three alkenes, which are gases, then we have liquids, and then the larger alkenes are normally solids. All right, so we look at isomers as well, which just shows us here that you change for alkenes or alkynes, you just change the location of your double bond, right? And then after you've changed all the possible locations of your double bond, then you start to have branches, right? So chemical properties of alkenes. So alkenes are much more reactive than, or alkenes are much more reactive than alkanes. That's because there is a double bond that can easily be broken for something to be added to it. So alkenes have an unsaturated carbon-carbon double bond, which are easily broken, which just said. Alkenes take part in many important chemical reactions and provide a basis for manufacturing of many important materials and chemicals in the industry. All right, so we have combustion of alkenes. So they undergo combustion in presence of oxygen to form carbon dioxide and water. All right, so alkenes do not burn as well as alkanes and generally produce more salty flame. All right, due to an insufficient supply of air, the combustion is incomplete, and carbon monoxide and salts are, which should be water. Right, so sometimes alkenes don't actually combust completely, right? If you have insufficient amount of oxygen, instead of producing carbon dioxide, it will produce carbon monoxide and water. And we know that carbon monoxide is dangerous to humans and environment on a whole, right? So if there is not enough oxygen present with alkenes, it will produce the carbon monoxide and water. If you have a lot, then it still produces carbon dioxide and water. All right, so it undergoes addition reaction because in this case, it can break the bond and add something without replacing a hydrogen. So alkanes are substitution because the hydrogen has to be removed, but for alkenes, there is just addition because we don't need to replace a hydrogen with anything. So we have halogenations. By the name, we notice that we just add in a halogen to the compound, right? So the reaction takes place quickly without the need of UV light or a catalyst. So alkenes react with so ethene can react with chlorine to form 1,2-dichloroethane, right? So if we have ethene here, right? So remember, ethene will have a double bond between its two carbons, right? If we break those two double bonds, then that means we have two available bonds that our chlorine can actually be bonded to. So it's Cl2, so one Cl goes on one and the next Cl goes on the next. So the name 1,2 means that on carbon 1 you have a chlorine, and on carbon 2 you have a chlorine, right? And the dye shows that it's both are the same thing, which is chlorine, right? So this type of reaction is an addition reaction because we're just adding without replacing, all right? And as I said, testing for unsaturated, right? So you use bromine water, right, which is just bromine added to the compound, right? So alkenes react with the aqueous bromine, which is called bromine water, and causes the solution to turn from brown to colorless, right? So alkenes or unsaturated compounds will actually change the bromine from its reddish color or brown reddish color to colorless, right? Or you can use potassium permanganate. So alkenes react with potassium manganate 7 solution in cold environments, or if the solution is acidified with dilute sulfuric acid, the purple solution becomes colorless. So if we have an alkene reacting with water with the permanganate and the acid, then we get a colorless solution to show that that's an unsaturated substance. If there's no color change, then that means it's not unsaturated. All right, so another type of reaction with alkenes are hydration. So hydration means the addition reactions with steam. So steam can be added to the alkene at about 300 degrees and 60 atmospheric pressure in the presence of phosphoric acid, which has a catalyst, right? And we get ethanol. So hydration means we're adding water, but the water is actually in the form of steam, right? So it has to be at high temperature in the presence of a catalyst, which is phosphoric acid, or sometimes it can be sulfuric acid, and it gives us an alcohol. So it gives us the equivalent alcohol of the alkene. So if it's ethene, it gives us ethanol. If it's propene, it gives us propanol, right? So it gives us the respective alcohol for the alkene that's there, because the OH from the steam will just bond with your alkene to give you that OH to form the alcohol. All right, and then final reaction is our hydrogenation. And by the name, it shows us that you're adding hydrogen to our compounds, right? So hydrogenation will give the alkenes change into your alkanes. So if you have ethene, then ethene will change to ethane, because now you're breaking that double bond and adding those two extra hydrogen that are needed to make ethene, right? So alkenes react with hydrogen in the presence of the catalyst nickel at a moderate high temperature to form its respective alkanes, right? So in this case, we need a catalyst of nickel and not a very high temperature. So not a low one, but not really a high one. So it's less than 300 degrees, right? In the presence of nickel, and you get the respective alkane, right? And also the alkenes, they can undergo what is known as polymerization, which we're going to look at later, right? Uses. So alkenes form based of petrochemical industries. They are used in starting materials on the manufacture of ethanol, which we just did too, right? Antifreeze that is used in car engines in temperate countries, solvents, detergents used as paints, used to make plastics, synthetic rubbers, and used in medicines as well. All right, and we just looked at how we distinguish between alkanes and alkenes, right, based on their reactions with bromine water. The alkanes will not change color, while alkenes will change it to a colorless solution, right? And also the combustion, alkenes can have incomplete combustion, and the flame actually is smoky flame. So it doesn't have a radiant flame, right? So that's the reactions of our alkenes. All right, so now let's look at alcohols. All right, so we know alcohols have the hydroxyl group, which are the OH groups. All right, so all we're doing is replacing a hydrogen from an alkene, all right, with a OH. So that's all alcohols are. All right, so properties of ethanol, which is the first alcohol that most persons will know. So ethanol is the most important alcohol in the homologous series. Only ethanol can be consumed. Right? So ethanol is a colorless liquid with a strong smell. It has a boiling point of 78 degrees Celsius and is volatile, meaning that it can burn. Right? It mixes readily with water. It is neutral to litmus. Right? So let's look at the chemical properties or reactions. So combustion. So alcohols burns in oxygen with a clean blue flame to form carbon dioxide and water. The reaction is exothermic and heat energy is given out. Hence, ethanol can be used as a fluid, as a fuel, sorry. Right? So alcohols or ethanol, they react with water to give with oxygen, sorry, to give carbon dioxide and water, and it also produces heat, right? So it's an exothermic reaction. So that's why you can have the E10 usage as fuel for cars, right? Because ethanol gives a certain amount of heat that can be used to fuel some machinery. Right? But it's not that enough to make pure ethanol be used as fueling for cars, right? So that's the reason why it mixed with the other gases, right? Next one is reaction with reactive metals. So when a small piece of sodium is dropped in some ethanol, the reaction steadily to give off bubbles of hydrogen gas, leaving behind a colorless solution of sodium ethoxide. Right? So what happened is that when it reacts with a reactive metal, and a reactive metal would be that any metal that's above hydrogen in your reactivity series, then what happens is it replaces the hydrogen from the OH bond, right? And it applies itself to it, right? So Na will remove hydrogen from it and takes the place of hydrogen, and so you get the sodium ethoxide and you get a hydrogen gas. So alcohols act like weak acids in this reaction. All right, next form is dehydration. Right, so dehydration now means, remember, one way of forming alcohols was to actually add water to alkenes. Right? Now, the opposite will happen if we have alcohol and we're taking away water from alcohol. So therefore, now we form alkenes. So dehydration of alcohol means that we're actually taking away the water aspect from alcohol. So we get back the respective alkene. Right? So if we have ethanol and we heat it, then we get water and we get the respective alkene, which is ethene. Right? So in doing this, we need sulfuric acid, and we need a temperature of approximately 170 degrees or 200 degrees Celsius. Right? So we need concentrated sulfuric acid at 170 degrees, passing ethanol vapor over active alumina at 450 degrees. So any of those two conditions will give you dehydration of alcohols. All right, so next reaction is oxidation. So if you add in oxygen to alcohols, then you actually now will give the acids, the carboxylic acid of that alcohol. So if ethanol is oxidized by hot acidified potassium dichromate solution into ethanoic acid. So we're adding the oxygen from a very strong acidified compound, preferably mostly used is the potassium dichromate. Then we get the carboxylic acid for the equivalent. So we had ethanol, so we get ethanoic acid, and we get water. All right, so during this reaction, the potassium dichromate is reduced, and the solution turns from orange to green in color. This reaction is used in the breathalyzer test used to detect drunken drivers. Right? So That's so the level at which the level of alcohol that's present will actually get a variation in your color change. And that variation in your color change is what they use to determine if you're above the alcohol content that you intake that you have, or you're below the alcohol intake. Right? So that's how the breathalyzer test detects if a driver is drinking too much or it's below the required limit, right? Because of the presence of the acidified potassium dichromate. When the alcohol reacts with it, it's going to change color to it's going to change from orange to a greenish color. Depending on the variation in the green, then you know if it's a high concentration or low concentration of alcohol that is present. All right, next type of reactions with alcohols are esterification. And esterification is where alcohols react with or a carboxylic acid to give us a compound known as esters. All right, so this is only able to happen if you have the presence of concentrated hydrochloric acid or sulfuric acid. All right, so you need a concentrated acid in order for this reaction to occur. So if we have ethanol reacting with ethanoic acid, the OH from our alcohol will be reacted with the H from our ethanoic acid. Right? So the OH from the alcohol reacts with the H from our acid to give us water. And now that free bond that is present can be now bonded together to give us the compound of the ester. Now, in naming the ester, right, we use the alcohol form first. Right, so we notice that the alcohol name comes first in our ester name. So the ethanol now changes to ethyl because, sorry, the acid first, sorry. So your acid comes first. So remember this, the H here is gone. So we have this present here, right? So we have ethyl because it's just two C's there. And then our alcohol, the ending of your alcohol now changes to 8 because all esters ends with a 8. So your alcohol ending, so the OL, because the OH is being removed, the OL is removed, right? Or just the L, sorry, and then you add 8 to it. So you have ethyl ethanoate. So your acid name comes first, then your alcohol name comes second. But if you notice the structure that is drawn, right, is the acid first, the alcohol. But when you're drawing the structure, you draw the alcohol first, then the acid. So esters are sweet smelling liquids which can be used for making perfumes and flavoring agents. Right, so esters also used to make soap. The process of making soap is also by using esters as well. All right, so this shows us how ethanol is formed. All right, we know that if we hydrate the alkene, we get the alcohol. All right, and that's how basically the process of ethanol is manufactured in the manufacturing industry. All right, so uses of ethanol. It's used for alcoholic beverages. It's used as a solvent, as a fuel, as noted before. Right. So those are the important part of esters. All right, so the final thing that we're going to look at today will be the acids. All right, so let's look at carboxylic acid. It's not a lot of things for it. And then that will be it for this lesson. All right, so we know carboxylic acid, it has a COOH group at the end. All right, so all their names ending with oic. So OIC for all their names. So if it's methane, then it's methanoic acid, right? So the E is removed and you put a OIC at the end. All right, so the ethanoic acid. So this ethanoic acid, it's two C's. because it's F, right? And then you have the COOH, and then everything else is being filled out by a hydrogen. All right, so physical properties of carboxylic acids. So organic acids are covalent compounds with a polar OH bond. The polarity of the OH bond is even greater when the alcohol than in alcohol because of the extra oxygen in the CO bond. This oxygen is highly electronegative and increases the pull of electrons away from the hydrogen in the OH group. The organic acids only exist in liquid and solid form and tend to have higher boiling points than the corresponding alcohols. The increased polarity of the OH bond makes organic acids extremely soluble in water. So because they are polar solutions, they are very soluble in water. All right, so organic acids are weak acids. They partially decomposes or dissociating when dissolved in water to give H plus ions. All right, so remember when we did acids, we looked at this part as well. So all organic acids are weak acids because they don't fully decompose in water. So the partially dissociation also makes them weak electrolytes for electrolysis. So organic acids reacts with metals, carbonates, bases, combustion, condensation, or esterification. Right? So it's an acid, so it reacts with the metal to give you a salt and hydrogen. It reacts with the carbonates to give you salt, water, and carbon dioxide. It reacts with a base to give you the acid and water. Right? So it still acts, gives you the general reactions with as acids, sorry. So in this case, we have an acid reacting with sodium. So we have ethanoic acid reacting with sodium. So we get sodium ethanoate and hydrogen gas. Right? So if it's ethanoic acid and sodium carbonate, then we get the sodium ethanoate, we get water and carbon dioxide. So the same reaction as any normal acids will have. Right? Same thing if it's an oxide or a hydroxide, gives you salt and water. It burns in air to give you carbon dioxide and water, just like alkanes. And then remember, it needed with alcohols to form or esters in the presence of concentrated sulfuric or hydrochloric acid. Right, so those are important stuff. All right, so uses. So these acids are very important in manufacturing a wide variety of things. So they are making various type of plastics or fabrics or films or paint. They're used in drugs like aspirins. They are bleaching agents in detergent, vinegar, which is used in cooking. Right? So those are important uses of or carboxylic acids. All right, so for next class, we'll be first starting off with some questions about all these functional groups, especially on the esters, since we didn't look deeply in the structures. All right, so we're going to have some little questions starting off with about these that we learned to ensure that we grasp these aspects fully. All right, so that's it for today, guys, and I'll see you guys in next class.